We're going to talk about the intermediate value theorem. Very important theorem in calculus. We're going to let f be a continuous function on the interval, the closed interval, from a to b. So without loss of generality, this is a fancy way of just saying we're going to pick one of these to be smaller than the other. Okay, so I'm going to have an interval from a to b. And then I'm just going to say, make my f of a less than my f of b. Okay, so that function output is going to be, for a, is going to be less than the function output for b. It could be flip-flopped or whatever, but we're just doing without loss of generality so that we can draw a picture. Okay, so let f be continuous. That means that I'm going to draw a curve without picking up my pencil, right? So if f is continuous on the closed interval a to b, then for every y value where y is between f of a and f of b, so what does that mean? So between these two values right here, there's some y value in there, okay, such that at least one value in c, where f of c, whenever I plug it in, I get the y value that I want. So what does that look like? So just pick a c, any c between a and b, and then if I plug that into my function f, the y value is equal to that f of c, and that y is stuck between those two values there. Looking at it through a picture, it looks pretty much like common sense, but this is a very powerful theorem. The intermediate value theorem is extremely important. Okay, so make sure that you're able to draw this picture and you understand if you have some continuous function here, then and you know that it's a closed interval and f of a is less than f of b, then you can find some x value between a and b so that the output, the y value, okay, is between those two values there. Very powerful when we're talking about finding roots, okay, because we spend a whole lot of time finding zeros of function solutions, right? So if I know that my function starts out negative and then it becomes positive, at some intermediate value, there is the point where the y value is equal to 0. And that's why it's extremely important for us, okay? So I'm going to explain why the function has a 0 on the interval from 0 to 1, okay? So this function right here is a cubic, and there is a theorem that says any cubic has at least one real solution. And it kind of makes sense with a cubic. You think about a cubic, cubics kind of look like this. So at some point they go from negative infinity to positive infinity. At some point they're going to have to at least cross the x-axis at least one time, maybe several. Okay? So we're going to show with the immediate value theorem why this works. Now to do this, what I need to do first is I need to compute, okay? So a 0, I need to know what it means to even be a 0. That means if I plug in some number in for x, some c, it outputs 0. That's what it means. So we're trying to show that there's some c value between 0 and 1 such this is true. Now we do this by using the intermediate value theorem. So to do that, I need to calculate the function values at the endpoints of the interval. So calculate f of b and f of a. So f of a here, I plug in 0. If I plug in 0 to my function, I get 0 cubed plus 3 times 0 minus 2 gets me negative 2. Okay? If I plug in 1, my f of b here, what do I get? Well, I get 1 cubed plus 1 times 3 minus 2. That gets me positive 2. So what do I know? I went from being negative to being positive. I went from negative to positive. So at some point, I had to pass the 0 line, okay? So I'm going to use this information to help me out. So what does it tell me? Then for every y value, so that f of a is less than y is less than f of b, what is the y we're trying to show here? The y is your 0, okay? So f of a is -2, okay, that's what we found there, is less than your 0, okay, that's what we're trying to show, why it has to have a 0. And that's less than your f of b, which is your 2. You see how we're literally using this definition here. Okay, so that's the f of 1, which it was the 2 that we found. Now, since this is true, since f of x is a polynomial, what do we know about polynomials? On their domain, they're continuous. So its domain is from -infinity to infinity, right? So we know that it's continuous for all, so it's definitely continuous on this interval that we're concerned with, 0 to 1. Okay. So by the intermediate value theorem, what does it say? It says there is at least one value c such that f of c equals the y value, which our y value here is 0, okay? Therefore, f of c equal to 0 for at least one value in 0 to 1, okay? Now, the thing that's kind of disappointing about the intermediate value theorem, think about this. It doesn't tell you what C is. All it does is says the intermediate value doesn't tell you the C value. All that it does is it says that there must be one C value that exists. Okay? That's the only thing that it tells you. Okay? It doesn't tell you that C equals, 0.25 or whatever that root is. We could find that root if we wanted to, right? But you could do it through calculator or whatever, right? So if I use my calculator, skip for now. Oh my goodness. Okay. So if I go to graph, so what is my function? My function is x cubed plus 3x minus 2. So x cubed and then plus 3x and then minus 2. Enter. If I go to graph this, I'm looking on this interval. I can do second calc, find the 0, left bound, right bound. Looks like my 0 is 0.87 or 897, so that makes sense. So the 0 here, the C here is 0.897 roughly. So that's clear. The intermediate value theorem didn't tell you that, but it does at least tell you that one exists, at least one. Could it be the case that more than one existed? Sure, for this particular function though, you can see from the graph that it only passes through the x-axis one time, okay? So it doesn't tell you the C value that makes it 0, but it does tell you that one exists, okay? So it's very, very powerful. An existence theorem is what this is known as. All right, guys. In the next video, we're going to talk about the bisection method and an application and actually finding out what that particular 0 is.